December 26, 1944. The snow-covered road south of Bastogne. Lieutenant Charles Boggis stood in the turret of his M4A3E2 Sherman, scanning the tree line through frozen breath that crystallized instantly in the -10-degree air. His tank, nicknamed Cobra King, carried 4 inches of frontal armor, twice the thickness of a standard Sherman. Behind him, a column of armor and infantry prepared to punch through 3 miles of German defenses to reach the surrounded 101st Airborne Division. The question that haunted American tankers throughout the Battle of the Bulge wasn't whether they would reach Bastogne. It was whether their tanks could survive the journey. German 88mm guns had been destroying Shermans with terrifying efficiency since Normandy. Every American tank crew knew the mathematics of their vulnerability. An 88mm round could penetrate 2 inches of armor at 1,500 yards. Standard Shermans had exactly 2 inches of frontal protection. The myth that emerged from Bastogne, repeated in countless post-war accounts, spoke of a miraculous metallurgical breakthrough that suddenly made Sherman armor invulnerable to German guns. The story claimed a single brilliant metallurgist had created an impossible alloy that transformed American armor overnight. It's a compelling narrative. It's also completely false. But the truth, the actual story of American armor metallurgy and what really happened at Bastogne, reveals something far more interesting than myth. It shows how American industrial thinking defeated German technical sophistication through unglamorous engineering excellence that no single person could claim credit for. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Sherman tank that broke through to Bastogne on December 26th carried no miraculous new alloy. Cobra King's armor was made from the same rolled homogeneous steel that every Sherman had used since 1942. The metallurgical composition hadn't changed. What had changed was how much of that steel protected the crew. The M4A3E2, designated Jumbo by crews who drove it, was born not from metallurgical innovation but from brutal field experience in the Norman hedgerows during summer 1944. June 1944. Normandy, France. Sherman tanks of the 2nd Armoured Division pushed into the bocage, that nightmare landscape of sunken roads, bounded by earth embankments topped with impenetrable hedgerows. German defenders had turned every field into a killing ground. Panzerfaust teams hiding in the hedgerows could approach within 50 yards before firing their shaped charge warheads. The high-velocity 75mm guns of Panther tanks knocked out Shermans at ranges exceeding 1,000 yards. American tank losses in the bocage exceeded 50% in some units. Crews began improvising protection desperately. They welded spare track links to hulls. They packed sandbags against armor plates. They poured concrete into wooden frames bolted to turrets. These field expedients provided psychological comfort more than real protection. But they demonstrated what crews wanted: more armor, regardless of the consequences for speed or mobility. Reports from Normandy reached the Aberdeen Proving Ground in Maryland by late June 1944. Engineers at Aberdeen had been tracking the Sherman vulnerability since North Africa. They understood the fundamental problem perfectly. German anti-tank guns had evolved faster than American armor. The solution seemed obvious: build Shermans with thicker armor. But thickness created cascading problems throughout the vehicle. Adding armor meant adding weight. Additional weight stressed the transmission, final drives, suspension, and engine. The Sherman's drivetrain had been designed for a 30-ton vehicle. Every additional ton of armor pushed components closer to failure. The engineering challenge landed on the desk of an obscure team at the Fisher Tank Arsenal in Grand Blanc, Michigan. No single metallurgist solved the problem because metallurgy wasn't the problem. The steel was fine. American rolled homogeneous armor, a chromium-molybdenum alloy containing roughly 0.4% carbon, 1% chromium, and 0.2% molybdenum, performed excellently within its design parameters. It resisted cracking and spalling better than German face-hardened armor. It could be welded reliably in field conditions. It maintained consistent protective qualities across varied thickness. The problem wasn't the steel's quality. The problem was quantity. How much armor could a Sherman carry before the drivetrain collapsed? Fisher tank arsenal engineers approached the jumbo development with characteristic American pragmatism. They didn't redesign the armor metallurgy. They redesigned the armor arrangement. The standard M4A3 had 2 inches of frontal armor, sloped at 56 degrees from vertical. This provided roughly 3.5 inches of effective thickness against perpendicular impacts. The jumbo would carry 4 inches of actual armor on the glacis plate, plus an additional 2-inch plate welded to the transmission housing. Total frontal protection reached 6 inches of actual thickness, providing roughly 10 inches of effective thickness when accounting for slope. The turret received similar treatment. Standard Sherman turrets had 3 inches of armor on the gun mantlet. Jumbo turrets mounted a massive 7-inch thick mantlet, the thickest armor on any American production tank. The entire turret casting was redesigned with 6 inches of frontal armor and 4-inch sides. The resulting turret weighed significantly more than standard Sherman turrets, requiring reinforced turret rings and modified traverse mechanisms. This brute force approach to protection violated every principle of elegant engineering. German designers would have rejected it immediately as crude and wasteful. They would have pursued exotic metallurgical solutions, face-hardening processes, or composite armor arrangements that provided maximum protection with minimum weight. American engineers didn't care about elegance. They cared about production. The jumbo used the same steel as every other Sherman, manufactured by the same suppliers using the same processes. No retooling was required. No new metallurgical expertise needed development. Fisher simply ordered thicker plates from the rolling mills and welded more of them together. The weight penalty was severe. A standard M4A3 weighed 33 tons. The jumbo weighed 42 tons, a 9-ton increase entirely from additional armor. Every component of the drivetrain now operated under loads 27% higher than design specifications. The Continental R975 radial engine that powered most jumbos produced 400 horsepower, unchanged from standard Shermans. The transmission, final drives, and suspension all came from standard production with minimal reinforcement. Engineers at Fisher expected catastrophic mechanical failures. They anticipated transmission breakdowns, final drive destruction, and suspension collapse. They prepared detailed failure analysis protocols to identify which components needed redesign. Then something remarkable happened. The jumbo didn't break. The Continental engine, designed with substantial safety margins for the 30-ton M4, handled the 42-ton jumbo without modification. The transmission, built using automotive industry practices that prioritized durability over theoretical optimization, functioned reliably under the increased load. The final drives, those herringbone gear assemblies that German engineers had dismissed as impossible to manufacture precisely, transmitted power without failure. The suspension required only significant modification. Standard Sherman bogies used vertical volute springs that compressed vertically under load. The jumbo received horizontal volute spring suspension, a heavier-duty system that distributed weight more effectively. This wasn't exotic engineering. It was simply stronger springs in a different orientation, components that already existed in the supply chain for other vehicles. Production authorization came in May 1944. The order specified 254 vehicles, a tiny fraction of total Sherman production. Fisher began building jumbos in June 1944, completing the production run by July. The first jumbos reached combat units in France during September 1944. They were immediately assigned to lead positions in armored columns, the point tanks that absorbed the first enemy fire, while lighter tanks maneuvered for flanking shots. Crews loved them despite significant drawbacks. The additional armor reduced maximum speed from 29 miles per hour to 22 miles per hour. The vehicle was nose-heavy, making it difficult to handle on slopes. The 7-inch gun mantlet restricted elevation and depression angles slightly. None of this mattered to crews who had watched friends burn to death in standard Shermans. The jumbo offered something no amount of tactical skill could provide: the ability to survive frontal hits from weapons that killed standard Shermans instantly. But even the jumbo couldn't stop an 88mm round reliably. German 88mm guns, whether the 8.8 cm KK-36 mounted on Tiger tanks or the 8.8 cm Park 43-towed anti-tank gun, fired armor-piercing rounds weighing roughly 25 pounds at muzzle velocities exceeding 2,600 feet per second. These projectiles carried enormous kinetic energy. At 500 yards, an 88 mm armor-piercing round could penetrate approximately 165 mm, or 6.5 inches, of vertical armor plate. The Jumbo's 4-inch glacis plate, sloped at 56 degrees, provided roughly 10 inches of effective thickness against perpendicular impacts. But 88 mm guns didn't fire perpendicularly in real combat. They fired from angles that reduced the protective benefit of slope. They fired armor-piercing capped rounds designed to grip sloped armor and prevent deflection. Ballistic testing at Aberdeen Proving Ground demonstrated the grim reality. An 88 mm Park 43 round could penetrate the Jumbo's glacis at ranges under 1,000 yards if the round struck at an angle approaching perpendicular. The 7-inch mantlet provided better protection, but even this could be defeated at close range by larger German guns. The 128 mm gun mounted on Jagdtiger tank destroyers could penetrate any armor on any Allied tank at any combat range. No metallurgical miracle protected Jumbo crews. They survived through statistical advantage. A Jumbo could absorb hits that would destroy a standard Sherman, giving crews time to return fire or retreat. Protection wasn't binary. It was probabilistic. The metallurgy myth emerged from an incomplete understanding of armor performance. Soldiers and journalists saw Jumbos survive hits that killed standard Shermans and assumed the steel itself must be different, better, special. The truth was simultaneously more boring and more impressive. American rolled homogeneous armor wasn't better than German armor metallurgically. It was better manufactured. German armor production during 1944 and 45 suffered from increasing quality control problems as strategic bombing disrupted supply chains and slave labor replaced skilled workers. German tanks received armor plates with inconsistent heat treatment, creating weak spots where hardness varied unpredictably. Some plates were too hard, shattering on impact. Others were too soft, failing to resist penetration adequately. American armor production maintained consistent quality throughout the war. The rolling mills at Carnegie Steel and Republic Steel had decades of experience producing high-quality alloy steel for commercial applications. They applied automotive industry quality control standards to armor production. Every plate received consistent heat treatment. Every batch underwent ballistic testing. Specifications were tight and enforced rigorously. This consistency meant American armor performed predictably. Engineers could calculate penetration resistance accurately. Crews knew what protection their vehicle provided. There were no metallurgical surprises, good or bad. The chromium-molybdenum alloy used in Sherman armor was entirely conventional. Chromium increased hardenability, allowing thicker plates to be heat-treated effectively. Molybdenum improved toughness, reducing the risk of brittle failure. Carbon content around 0.4% provided optimal balance between hardness and ductility. This composition had been standard in American armor plate since the 1930s. No innovation occurred during the war because none was needed. The metallurgy worked. What did improve was the manufacturing process. Early Sherman hulls were assembled from multiple cast and rolled armor sections welded together. Each weld line created a potential weak point. Later, production simplified hull construction dramatically. The large hatch hull, introduced in early 1944, used a single rolled plate for the entire glacis. This eliminated welds and improved structural integrity. The change wasn't driven by metallurgical insight, it was driven by production efficiency. Welding was slow and expensive. A single large plate was faster and cheaper to install. That the change also improved armor performance was a welcome bonus, not the primary goal. Cast armor presented different challenges. The M4A1 variant used a cast upper hull, formed by pouring molten steel into enormous sand molds. Casting allowed complex shapes impossible to create with rolled plate, but introduced consistency problems. Cooling rates varied within the casting, creating areas of different hardness. Shrinkage during cooling sometimes created voids or inclusions. Quality control required X-ray inspection of every casting, a time-consuming and expensive process. Despite these challenges, cast armor performed adequately. It was slightly less effective than rolled armor of equivalent thickness, perhaps 10 to 15% weaker against penetration, but it was much faster to produce. Factories without expensive rolling mills could produce cast hulls. This production flexibility mattered more than the slight performance penalty. The Jumbo's armor was entirely rolled plate, not cast. This choice reflected Fisher Tank Arsenal's manufacturing capabilities and the desire for maximum protection. Rolled plate provided the best performance per inch of thickness. For a vehicle where every millimeter of armor mattered, rolling was the obvious choice. No new metallurgical process was involved. Fisher ordered thicker plates from the same suppliers producing plates for standard Shermans. The steel came from the same heats, made to the same specifications, tested by the same methods. December 23, 1944, Luxembourg, near the German border. Lieutenant Charles Boggess received command of Cobra King after the previous commander, Captain Charles Trover, was killed by a German sniper. Boggess was 23 years old, a 1943 graduate of the tank officer course at Fort Knox. He had joined the 37th Tank Battalion in September 1944, arriving just as the Jumbos were being distributed to combat units. In the 3 months since, he had learned to appreciate the Jumbo's protection while cursing its limitations. The Battle of the Bulge had erupted on December 16th when German forces launched a massive offensive through the Ardennes forest. American lines, weakly held by inexperienced divisions resting after the brutal fall campaign, collapsed under the assault. German armor poured through the gaps, racing west toward the Meuse River and ultimately Antwerp. The town of Bastogne, a critical road junction, became surrounded by German forces on December 20th. The 101st Airborne Division, rushed to Bastogne by truck, dug in to defend the town. They would hold for 7 days without resupply, under constant attack, in weather that grounded Allied aircraft and prevented aerial resupply. General George Patton, commanding Third Army to the south, received orders to relieve Bastogne. His response became legendary. He claimed he could attack north within 48 hours with 3 divisions. Staff officers thought this impossible. Patton proved them wrong. On December 22nd, Third Army attacked northward through brutal winter weather and determined German resistance. The 4th Armoured Division, spearheading the attack, covered roughly 20 miles in 4 days. That might seem slow, but the division was fighting continuously, against well-positioned defenders, in conditions that turned roads to ice and reduced visibility to yards. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By December 26th, the 4th Armoured Division was within 5 miles of Bastogne. The 37th Tank Battalion received orders to make the final push. The attack would go through the village of Assenois, held by German paratroopers of the 5th Fallschirmjäger Division. Intelligence reported anti-tank guns, machine gun positions, and at least one Panzer IV tank defending the approaches. The plan was characteristically American, direct and violent. Artillery would pound Assenois for 15 minutes. Then tanks and infantry would charge straight through the village without stopping, relying on speed and firepower to overwhelm defenders before they could organize effective resistance. Cobra King would lead. Boggess received explicit orders. Drive through Assenois at maximum speed. Do not stop for anything. If the tank ahead of you is hit, drive around it. The objective is Bastogne, not Assenois. Everything else is expendable. The attack began at 4:15 p.m. on December 26th. Supporting artillery fire lifted at 4:30. Cobra King lurched forward, accelerating to its maximum speed of roughly 22 miles per hour. Behind it came 8 more Shermans, a mix of standard M4A3S and 1 other jumbo. Half-tracks carrying infantry from the 53rd Armoured Infantry Battalion followed close behind the tanks. The charge through Assenois became a confused melee. German defenders, stunned by the artillery barrage but still functional, opened fire from buildings and foxholes. Panzerfaust teams emerged from cellars as the tanks roared past. Machine gun fire raked the half-tracks. The infantry bailed out and fought house to house while the tanks continued forward. Cobra King took multiple hits during the passage. One round struck the right track, damaging several links but not breaking the track. Another round, possibly from a Panzerfaust, struck the turret at an oblique angle and deflected without penetrating. A third round hit the glacis plate and ricocheted into the sky, leaving a bright scar across the armor but causing no damage. These hits would have destroyed a standard Sherman. The Panzerfaust warhead, with its shaped charge design, could penetrate 4 inches of vertical armor. But the hit on Cobra King struck at such a steep angle that the weapon's penetration capability was insufficient. The 88mm round, if that's what struck the glacis, hit at an angle that maximized the armor's effective thickness. Slope saved Cobra King more than any metallurgical property. The armor's quality ensured it didn't shatter or spall when hit, but the geometry of the impacts determined whether penetration occurred. 4 Shermans were knocked out during the charge through Assenois. 3 were standard M4A3S. 1 jumbo was hit in the side where armor was only 2 inches thick, not enough to stop German anti-tank weapons. The column continued forward, leaving the burning tanks behind. North of Assenois, the tanks encountered scattered German positions. Bulge led his remaining tanks cross-country, avoiding roads where anti-tank guns might be emplaced. They approached a fortified position and destroyed it with high-explosive shells. They passed groups of Germans who appeared confused by the sudden appearance of American armor so far forward. At 4:50 p.m., Cobra King made contact with forward elements of the 101st Airborne Division. A soldier emerged from a foxhole as Bulge's tank approached. Bulge, wary of German infiltrators dressed in American uniforms, demanded identification. The soldier identified himself as a member of the 326th Airborne Engineer Battalion. The siege of Bastogne was broken. The psychological impact exceeded the tactical significance. The garrison had held for 7 days, convinced they were surrounded and alone. The sudden appearance of tanks from Patton's Third Army proved the line hadn't collapsed, that American forces could still coordinate and execute complex operations, that German momentum was broken. Cobra King's role in this achievement had nothing to do with miraculous metallurgy and everything to do with additional armor thickness applied through conventional manufacturing. The tank survived not because its steel was better, but because it had more steel in the right places, arranged at angles that maximized effective thickness. The myth of a single metallurgist creating an impossible alloy misunderstands how military technology actually develops. Innovation in armor protection came from thousands of engineers, metallurgists, production workers, and soldiers making incremental improvements based on field experience. No individual genius solved armor protection. The entire American industrial system solved it through unglamorous process improvement and brute force application of adequate materials. The real metallurgical story of American armor wasn't about breakthroughs. It was about consistency at a far less dramatic but infinitely more impressive achievement. By 1944, American steel mills were producing armor plate at rates that would have seemed impossible before the war. The Carnegie Illinois Steel Corporation's Irvin Works in Pennsylvania rolled armor plate 24 hours per day, 7 days per week. Republic Steel's plant in Massillon, Ohio, operated on the same relentless schedule. Between them, these 2 facilities produced roughly 60% of all American tank armor. The process began with electric arc furnaces that melted scrap steel and alloying elements into precise compositions. For armor plate, specifications called for 0.3 to 5 to 0.4 to 5% carbon, 0.8 to 1.2% chromium, and 0.1 to 5 to 0.3% molybdenum. Manganese, silicon, and trace elements rounded out the composition. Each heat, typically 200 tons of molten steel, underwent spectrographic analysis before pouring. If composition fell outside specifications, the heat was adjusted by adding alloying elements or diluted with low alloy steel. This quality control happened before any steel solidified into ingots. Once poured, ingots cooled slowly in insulated pits that maintained elevated temperatures for days. This slow cooling prevented the formation of internal stresses that would cause cracking during subsequent working. After cooling, ingots were reheated to rolling temperature, approximately 2,200 degrees Fahrenheit, and passed through massive rolling mills that squeezed the steel into progressively thinner sections. For a 2-inch armor plate, the process required multiple passes through rollers that applied thousands of tons of pressure. Each pass reduced thickness while elongating and widening the plate. The rolling process wasn't merely shaping steel, it was restructuring the metal's grain structure, aligning crystals in ways that improved toughness and resistance to cracking. After rolling to final thickness, plates underwent heat treatment, the critical step that determined armor performance. Plates were heated to approximately 1,500 degrees Fahrenheit and held at that temperature long enough to ensure uniform heating throughout the thickness. Then they were quenched, plunged into enormous tanks of oil that cooled the steel rapidly. This rapid cooling locked the steel's crystalline structure in a hard, strong configuration, but quenched steel was also brittle. The final step, tempering, involved reheating the plate to approximately 800 degrees Fahrenheit and holding it there for several hours. This relieved internal stresses while maintaining most of the strength gained during quenching. The resulting armor had optimal balance between hardness and toughness. Every plate underwent ballistic testing before shipment. Test facilities maintained batteries of German and American anti-tank guns that fired at sample plates cut from each production batch. If a plate failed ballistic requirements, the entire batch was rejected and returned to the mill for reprocessing. This ruthless quality control ensured consistent performance. American tank crews could trust that their armor would perform as specified. German tank crews enjoyed no such confidence by late 1944. German armor production faced challenges American industry never encountered. The loss of critical alloying materials forced German metallurgists to develop substitute compositions. Molybdenum, essential for toughness in armor steel, came primarily from mines in Norway and imports from overseas. Allied control of shipping lanes cut off imports. Norwegian resistance and Allied bombing disrupted Norwegian production. By mid-1944, German armor plate contained minimal molybdenum, replaced partially by increased chromium and vanadium content. These substitutions worked in theory. In practice, they created armor with unpredictable properties. German armor also suffered from inadequate heat treatment as fuel shortages limited furnace operations and Allied bombing disrupted facilities. Panther tanks produced in late 1944 frequently had glacis plates with inconsistent hardness across their surface. The center might be properly hardened while edges remained too soft, or the reverse, with over-hardened edges that shattered on impact while the center performed adequately. This inconsistency resulted from interrupted quenching procedures, where plates were lifted in and out of quench tanks multiple times, instead of being submerged continuously. The technique saved fuel, but created metallurgical problems. American metallurgists knew about these German difficulties through intelligence reports and examination of captured vehicles. They understood that American armor's advantage wasn't superior alloy design, but superior manufacturing control. This knowledge informed a critical decision about the Jumbo program. Rather than attempting exotic metallurgical solutions that might improve protection by 10 or 15% while introducing production complexity, engineers simply specified thicker plates of proven composition. This decision reflected deep understanding of industrial warfare. Theoretical improvements meant nothing if they couldn't be produced reliably at scale. The metallurgist who came closest to the myth of a single innovative genius was probably Dr. Edgar Bain of the United States Steel Corporation. Bain had spent decades researching steel metallurgy and held numerous patents on heat treatment processes. During World War II, he served as a consultant to the War Department on armor plate production. His contributions included refined heat treatment protocols that improved consistency and reduced rejection rates. But Bain developed no miracle alloy. His work involved incremental optimization of existing processes, the unglamorous engineering that rarely produces headlines but wins wars. Another key figure was Captain George Hogue of the Army Ordnance Department's Ballistic Research Section. Hogue coordinated testing programs that compared American and German armor performance. His reports documented that American rolled homogeneous armor provided roughly equivalent protection per inch of thickness as German face-hardened armor, despite the German armor's higher surface hardness. This finding validated American manufacturing approaches and discouraged pursuit of face-hardening techniques that were expensive and difficult to control. Hogue's work ensured American industry focused resources on proven methods rather than chasing marginal improvements. The Aberdeen Proving Ground in Maryland became the center of American armor research. Here, engineers tested captured German vehicles to understand enemy capabilities. They fired American and German weapons at armor samples to develop penetration tables. They investigated novel armor arrangements, including spaced armor, where two thin plates separated by air gaps provided better protection than a single plate of equivalent total thickness. This research produced the M26 Pershing heavy tank, with thicker armor and a more powerful 90mm gun. But the Pershing arrived too late to significantly impact the war. Only 20 Pershings reached Europe before Germany surrendered. The decision to prioritize Sherman production over Pershing development remains controversial. The Pershing offered superior protection and firepower. It could engage German heavy tanks on roughly equal terms, but it weighed 46 tons, significantly more than the Sherman's 33 tons. This weight created logistical challenges. Bridges that could support Sherman columns would collapse under Pershing weight. Tank transporters couldn't carry Pershings over long distances. Port facilities needed modification to handle the heavier tanks. Most critically, Pershing production would have required retooling factories, reducing total tank output for months during the transition. General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, faced this decision repeatedly during 1944. His staff prepared studies showing that immediate Pershing production would reduce available tank strength by approximately 40% for 6 months while factories retooled. During those 6 months, German forces might exploit the reduced American armor strength to prolong the war. Eisenhower chose to maintain Sherman production, accepting that individual Shermans were inferior to individual German tanks, but confident that American numerical superiority and superior logistics would prove decisive. Events validated his judgment. Germany surrendered in May 1945, roughly 6 months after the Pershing debate reached its peak. Had Eisenhower chosen Pershing production, American tank strength during the Battle of the Bulge would have been significantly reduced, potentially altering the campaign's outcome. The metallurgical reality of Sherman armor was simultaneously mundane and extraordinary. The steel itself was ordinary, a chromium-molybdenum alloy that any competent metallurgist could specify. What was extraordinary was producing that steel consistently in vast quantities while maintaining quality control. American steel mills produced approximately 200,000 tons of armor plate during World War II. This steel went into tanks, tank destroyers, armored cars, half-tracks, and various other armored vehicles. Every ton met specifications. Rejection rates remained below 5% throughout the war. No other combatant nation achieved comparable consistency at comparable scale. This industrial achievement rested on foundations built decades before the war. American steel industry had developed sophisticated quality control methods during the 1920s and 30s. Statistical process control, pioneered by Walter Schuhart at Bell Laboratories, allowed manufacturers to monitor production continuously and detect problems before they produced defective material. American steel mills employed thousands of quality control inspectors who measured dimensions, tested hardness, and verified composition continuously. This infrastructure couldn't be replicated quickly. Germany attempted to match American quality control methods, but lacked the trained personnel and testing equipment to implement them effectively. The Sherman's armor also benefited from American welding expertise. Early Sherman hulls used riveted construction, similar to pre-war designs. Rivets created weak points where armor plates joined. Impact near a rivet line could shear rivets, causing them to fly through the crew compartment as deadly projectiles. Welding eliminated this problem but created new challenges. Poorly executed welds were weaker than the parent metal. Heat from welding altered the metallurgical structure of the armor plate near the weld, creating heat-affected zones with different properties than the rest of the plate. American shipbuilding industry had developed sophisticated welding techniques during the 1930s. Liberty ship production applied these methods at unprecedented scale, welding ship hulls instead of riveting them. The same expertise transferred to tank production. Welders learned to control heat input, preventing excessive heating of parent metal. They learned to prepare joints properly, ensuring complete penetration and strong fusion. They learned to inspect welds using X-ray equipment that revealed internal defects invisible to surface inspection. By 1944, American welding had evolved into a science supported by extensive research and rigorous training. German armor production never achieved comparable welding quality. German Panthers used welded hulls, but weld quality varied significantly between factories and even between individual vehicles from the same factory. Some Panthers had excellent welds that performed well under combat stress. Others had welds that cracked under shock, causing armor plates to separate partially. This inconsistency reflected Germany's reliance on increasingly unskilled labor, as experienced workers were conscripted for military service. American factories maintained skilled workforces throughout the war, exempt from conscription because their industrial contributions exceeded their potential military value. The jumbo's welded construction required exceptional welding skill. Joining the 4-inch armor plate demanded high heat input and multiple passes to achieve complete penetration. Each weld had to be executed perfectly, because any defect created a weakness in the vehicle's primary protection. Fisher Tank Arsenal employed welders who had trained for months on progressively more difficult joints before being certified for armor welding. They worked from detailed procedures that specified electrode types, current settings, travel speeds, and inspection criteria. Every weld underwent visual inspection and a percentage received X-ray or ultrasonic inspection to verify internal quality. This attention to detail extended throughout Sherman production. Engine installations followed precise torque specifications for every bolt. Electrical systems used color-coded wiring with detailed schematics. Transmissions were assembled in clean rooms to prevent contamination. Final drives received individual testing before installation. Nothing was left to chance or operator judgment. This systematic approach reflected American manufacturing philosophy developed in automotive plants over decades. It worked because it reduced complexity to repeatable procedures that could be executed reliably by trained workers following clear instructions. German tank production retained more craft elements where individual worker skill determined quality. This approach produced excellent results when skilled craftsmen were available, but as the war progressed and skilled workers became scarce, quality suffered. American approach, de-skilling work through detailed procedures and specialized tooling, maintained quality even as worker experience declined. By 1945, American factories were producing tanks with workers who had mere months of experience, maintaining a quality that German factories with experienced workers struggled to match. The bitter winter of 1944 to 1945 tested armor metallurgy in ways peacetime research never anticipated. Steel becomes more brittle at low temperatures. The ductility that prevents catastrophic cracking decreases as temperature drops. At -10 degrees Fahrenheit, typical during the Battle of the Bulge, steel has roughly 60% of its room temperature toughness. This means armor more susceptible to cracking on impact. German armor, with its inconsistent heat treatment, suffered badly in extreme cold. Panthers fighting in the Ardennes experienced armor cracking from impacts that would have been defeated at warmer temperatures. The cracks didn't penetrate fully, but created spalling where pieces of armor broke off the interior surface and wounded crews. American armor proved more resistant to cold temperature cracking. The consistent heat treatment and slightly lower hardness provided better performance across temperature ranges. Sherman crews reported fewer instances of spalling compared to crews of captured Panthers used by American forces for evaluation. This difference, modest in absolute terms, could mean survival versus injury for crew members. It represented another incremental advantage from superior manufacturing control rather than superior metallurgical design. Testing after the war confirmed these field observations. Aberdeen Proving Ground conducted extensive cold-weather ballistic tests, firing at armor samples cooled to various temperatures. American rolled homogeneous armor maintained its resistance to cracking better than German face-hardened armor at temperatures below freezing. The American armor's lower surface hardness and higher core toughness provided better performance when brittleness from cold reduced overall material properties. This wasn't because American metallurgists had designed armor specifically for cold weather. They had simply produced well-balanced armor that performed predictably across a range of conditions. January 1945. The Battle of the Bulge was ending. German forces, having advanced 60 miles into Belgium, were being pushed back toward their start lines. The offensive had failed to reach its objectives. American forces had held critical positions, disrupted German timetables, and ultimately contained the penetration. The cost was brutal. American forces suffered approximately 80,000 casualties. German casualties exceeded 100,000. Tank losses on both sides were staggering. The 4th Armored Division alone lost more than 100 tanks during its advance to Bastogne and subsequent operations. Cobra King survived the war. After breaking through to Bastogne, the tank remained in combat through February and March 1945. The crew was changed as casualties and rotations cycled personnel through combat units. The tank itself underwent field maintenance multiple times, replacing damaged components and worn parts. In February, Cobra King received an upgrade, swapping its original 75mm gun for a 76mm high-velocity gun that provided better armor-piercing capability. This conversion, applied to roughly 100 jumbos during early 1945, gave the heavy assault tanks firepower more appropriate to their protection level. The jumbo program, modest in scope with only 254 vehicles produced, demonstrated American industry's ability to respond to combat requirements rapidly. From initial combat reports in June 1944 to first deliveries in September was barely 90 days. This response time reflected the flexibility of American manufacturing. Factories could modify production without complete retooling. Suppliers could provide thicker plates without developing new capabilities. The entire industrial system could pivot to address changing requirements while maintaining output of standard vehicles. German industry lacked this flexibility by 1944. Panther production, for example, was optimized to the point where modifications became extremely difficult. Changing armor thickness would require new casting patterns, modified welding fixtures, and altered assembly sequences. The time and resources required for such changes exceeded what German industry could afford, while under constant air attack and material shortages. German forces fought with the equipment they had, unable to adapt significantly to changing combat conditions. American forces continuously incorporated improvements based on combat experience, maintaining technological relevance throughout the war. The myth of the miracle metallurgist persists because it fits comfortable narrative patterns. Wars are won by brilliant individuals making breakthrough discoveries, but World War II wasn't won by brilliant individuals. It was won by competent organizations, executing well-understood processes reliably at scale. The metallurgists who developed Sherman armor specifications were skilled professionals applying established principles. The engineers who designed jumbo modifications were experienced practitioners solving straightforward problems. The workers who built the tanks were trained technicians following detailed procedures. None were geniuses. All were competent. Competence at scale proved more valuable than genius in isolation. This lesson applies beyond metallurgy and armor. American success in World War II resulted from systemic advantages, not individual breakthroughs. The industrial base, built over decades, could produce vast quantities of adequate equipment. The education system provided a workforce capable of learning complex technical skills. The scientific establishment could solve problems systematically through research and testing. The transportation network could move materials and products efficiently. No single element was decisive. The combination of all elements created an overwhelming advantage. German forces often possessed superior individual weapons. The Panther tank was better armed and armoured than the Sherman. The Messerschmitt Me-262 jet fighter was faster than any Allied aircraft. The Type XXI submarine was quieter and more capable than American submarines, but Germany couldn't produce these weapons in sufficient quantities while maintaining quality. Superior individual weapons mattered less than adequate weapons in overwhelming numbers. American industry understood this calculus. Sherman designers accepted inferiority in one-on-one comparisons because they knew battles were won by the side that could field more tanks, supply them reliably, maintain them effectively, and replace losses continuously. The armour on Cobra King was no different than the armour on every other jumbo. It was no different than the armour on standard Shermans, except for thickness. No metallurgical innovation separated Cobra King from tanks built 2 years earlier. What separated it was 4 inches of armour plate instead of 2 inches, applied through straightforward manufacturing. This solution lacked elegance. It represented brute force engineering, solving problems by adding material rather than optimizing design. But it worked. Cobra King broke through to Bastogne and survived the war. The crews who fought in it came home. That was the only metric that mattered. Post-war analysis of German armour confirmed what wartime testing had suggested. German face-hardened armour, with its extremely hard surface layer and softer core, performed excellently against blunt-nosed projectiles that failed to penetrate the hard face. But Allied armour-piercing rounds increasingly used caps, soft steel tips that deformed on impact and prevented shattering of the projectile before penetration could occur. Against capped projectiles, German face-hardened armour provided minimal advantage over homogeneous armour of equivalent thickness. The complex manufacturing process required for face hardening yielded little benefit in actual combat. American rolled homogeneous armour, simpler to manufacture and more consistent in quality, proved the superior solution for mass-produced tanks. It didn't excel in any particular aspect of armour performance. It was adequate in all aspects. This adequacy across multiple dimensions proved more valuable than excellence in one dimension at the cost of weakness in others. The same principle applied throughout Sherman design. Adequate armour, adequate firepower, adequate mobility, excellent reliability, and overwhelming numbers defeated superior German tanks that broke down, ran out of fuel, or couldn't be replaced when destroyed. The post-war years saw continued evolution of armour, technology. Composite armours, combining different materials to defeat shaped charge warheads, emerged in the 1950s. Cobra armour, developed in Britain during the 1960s, used layers of ceramic and metal to provide protection far exceeding rolled steel of equivalent weight. Modern tanks use reactive armour that explodes outward when hit, disrupting incoming projectiles before they penetrate. These innovations represent genuine breakthroughs in armour protection, but they built on foundations established during World War II, when American industry learned to produce consistent armour at scale. The engineers and metallurgists who developed Sherman armour never received public recognition. Their names don't appear in history books. No monuments commemorate their contributions. They worked in anonymity, solving technical problems, and managing production processes. But their collective achievement, producing consistent armour plate for thousands of tanks, enabled Allied victory as surely as any battle. The soldiers who rode those tanks into combat trusted that the armour would perform as designed. That trust, earned through consistent quality, allowed tactical boldness that German crews couldn't match because they never knew if their armour would perform reliably. Cobra King sits today in the National Museum of the United States Army in Fort Belvoir, Virginia. The tank underwent restoration after decades of outdoor display in Germany. Restorers cleaned decades of corrosion, repaired damaged components, and repainted the vehicle in wartime markings. The chalked inscription, first in Bastogne, was carefully reproduced on the hull side. Visitors can see the impact scars where German rounds struck and failed to penetrate. Those scars tell the real story of Sherman armour, not miraculous metallurgy, but adequate thickness applied through manufacturing competence. The museum placard describes Cobra King's role in relieving Bastogne. It mentions the jumbos, thicker armour. It names Lieutenant Bulge and his crew. But it doesn't mention metallurgists, because no individual metallurgist deserves credit. The armor that protected Cobra King resulted from organizational competence spanning the entire American steel industry. Ore miners in Minnesota extracted iron ore. Limestone quarries in Michigan provided flux. Coal miners in Pennsylvania provided coking coal for blast furnaces. Railroads transported materials to mills. Electric utilities powered furnaces. Alloying element producers supplied chromium and molybdenum. Rolling mills shaped ingots into plates. Heat-treating facilities hardened the steel. Inspectors verified quality. Transporters delivered plates to tank factories. Every step executed competently. No step required genius. All steps required competence. This unglamorous reality explains why the miracle metallurgist myth persists. People want heroes, individuals to credit for victory. The truth offers only organizations, processes, and systems. But systems won World War II. The American system for producing armor plate exceeded the German system. The American system for building tanks exceeded the German system. The American system for training crews, supplying units, maintaining vehicles, and replacing losses exceeded German systems. Individual brilliance mattered far less than systematic competence. The metallurgical lesson from Sherman armor development applies to countless modern challenges. Complex problems rarely yield to individual genius. They yield to organizational competence, systematic problem-solving, rigorous testing, continuous improvement, and relentless attention to detail. These qualities lack drama. They don't produce compelling narratives, but they produce results. American armor metallurgy during World War II achieved no breakthroughs. It simply executed well-understood processes consistently at unprecedented scale. That consistency, that reliability, that predictability proved more invaluable than any miracle alloy could have been. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.